Well, we just finished talking about the problems with adding too much water to concrete. And if you've ever been part of a field crew trying to place concrete, you know, like I said, the main reason people do this is they want to wet the concrete up and make it easier to place. It just flows better because it's not so stiff. But again, remember, the higher the water to cement ratio in that concrete, the lower the strength. And also remember that we've talked about the hardening of the concrete being that chemical process we called hydration, and we discussed a few of the chemical admixtures that we can use these days to change the properties of the concrete, like the water-cement ratio. Now, one of the chemicals that we discussed was the water-reducing admixture that changes the properties of the plastic concrete to make it more flowable without adding more water. What I want to introduce now is what we're calling self-consolidating concrete. Now, this is a revolutionary new product. It uses one or more chemical admixtures to make a plastic concrete that's completely flowable. It requires almost no effort to place. This is incredible stuff because it flows like a very fluid liquid right out of the mixer chute instead of being stiff and piling up like it would without the chemicals in it. In fact, it's so fluid that one of the tests that we use in the field for quality control won't work on self-consolidating concrete. We used to, on regular concrete, we'd measure what we call the slump of the concrete. And this is a field test that measures the stiffness of the concrete and compares it against what we expected it to be according to the mix design. And in that test, we would fill a 12-inch tall cone called the slump cone with fresh plastic concrete, and then we'd lift that cone and measure how much the pile fell or slumped. Now, without any chemicals added to the mix, a concrete with a typical water-cement ratio that we'd use in the field would slump probably about 4 inches. Or in other words, when we lift that cone, that 12-inch tall pile of concrete would slump down to an 8-inch tall pile of concrete. Now, with self-consolidating concrete, that same test wouldn't give you any usable information because the concrete is so flowable. So they revised the test a little. We're going to use that same cone, but we're going to turn it over. We're going to invert it and fill that with concrete. Now when the cone's lifted and the concrete just flows out the bottom, they actually measure the spread or the size of the pile instead of the height of the pile. The height at that point is nothing more than the biggest size rock being used in the mix. That's how flowable it is. Now, when they do this test, they're also looking for a nice round pile or patty as the concrete flows away from the cone, and they're looking to see that all the rocks stay evenly distributed throughout that pile. And that's really one of the incredible properties of this mixture that makes it work. So even though the concrete flows like water, the aggregates stay properly distributed all throughout that mix. I can tell you, if this same test was done with just a really watered down mix, you'd just have a big pile of rocks in the middle with watery paste flowing away from that pile of rocks. And this would translate to what would end up being a very weak concrete mix. Now, in use, this product requires very little handling, again, because it just flows into the forms and levels itself off. It's that flowable. Now, not only does it require very little effort to rake into place, it requires almost no effort to vibrate it, to get it consolidated. And what I mean by this is that with regular concrete, I usually have to vibrate it to get it consolidated around the reinforcing and into the corners, and I had to be careful not to over-vibrate, which could also separate the aggregates from the paste. So when I cast something like a concrete wall or a column, the finish or the smoothness, once the concrete hardens and the forms are removed, really depended heavily on proper vibrating. Now, with self-consolidating concrete, the issue of consolidation by vibration virtually goes away. If I use this correctly, we'd really try to pump something like a wall from the bottom up and let that plastic concrete flow and fill up the forms, covering all the reinforcing as it goes. Or in the case of something like a long beam, we'd place the concrete over from one end, almost pushing it through the forms as it flows. Now, with regular concrete, it would be so stiff that this would never work. We just end up with a big pile of concrete. But with this stuff, it's so flowable that it just consolidates itself without vibration when it moves. And when the forms are taken off, we just end up with a better finish than we would with regular concrete. All right, now there's a cost to you doing this. You do pay extra for these chemicals that make it so flowable and that hold these aggregates in place. And you do have to know how to work with this material since it acts so differently when it's being placed than traditional concrete. But sometimes these costs and considerations can be offset by other factors. So in a precast plant, for example, it saves all kinds of labor, and it saves all the energy that we would otherwise use to run those vibrating casting beds that we use at a precast yard. Now, sometimes this alone is enough to offset the cost of those chemicals. On some projects, there can be an incredible amount of congestion inside the forms with all the reinforcing steel that might be needed. And in these cases, self-consolidating concrete might represent a better way to actually get the concrete placed and consolidated properly. Now, this stuff's been around for a little while, but it's really only more recently that more companies have had some real success in getting all the proportioning just right, so the product really works in a cost-effective manner. So now that you've seen some really cool uses of chemicals and admixtures and how they can change the properties of both the plastic concrete and the final hardened concrete, let's go ahead and move on. We're going to take a look at some of the strengths and weaknesses of this building material itself.